All right, let's go ahead and kick things off today with this lecture survey question. Most folks did not get this one right, but I think there's some close answer choices here to think about. So let's go ahead and take a look. Question asks, which of the following properly constructs the Lagrangian for the short run profit maximization problem, not the cost minimization problem? For a firm whose technology is given by Q equals F of K of L, facing output and input prices of P, W, and R, and using capital equal to K bar in the short run. And the correct answer, which about 20% of the respondents got, is this top one up here. Okay. Note the first part of it in the orange box is measuring what? What's that first part there? What is that thing? Yeah, that is the profit, right? That is exactly the level of profit, which is our objective function. Okay, note that's also in choice B. It looks like there's a profit function. Okay. But C and D, those are not profit functions. Those are what? Yeah, those are look like costs, right? That's the expenditure on the inputs. In fact, C and D, those would be the Lagrangian in C if we were doing short run cost minimization, and D if we were doing long run cost minimization. B is not the right answer here because it does not incorporate the short run constraint, K bar. Right? So B would be a long run profit maximization problem. But A is the one we are looking for. We have a multiplier for the technology constraint. We have a second different multiplier for the short run capital constraint, where capital has to equal K bar. So if you got that one right, nicely done. Otherwise, we're going to shift gears and pick up about where we had left off last class, discussing our short run profit maximization in terms of characterizing that solution. For a one-dimensional problem, which we had seen last time, we could actually write two different ways. We could write the problem out in terms of what's the profit maximizing input usage, or we could write the problem out in terms of what is the profit maximizing output level. So what we're going to do today is we're going to continue our discussion of both the first and second order conditions associated with the short run profit maximization problem. We're going to make sure that we can identify profit and loss situations diagrammatically. And in doing so, we're going to review the short run shutdown rule that you should be familiar with from Econ 1, but you may not have seen it for a while. And we're going to wrap things up by deriving the short run supply curve. And that is the big aha moment in this course, similar to 100A, where in 100A, you used a utility maximizing budget constrained consumer to explain where a demand curve comes from. We are using a technology constrained profit maximizing producer to explain where the supply curve comes from. So if we get any farther in the slides than what you have access to, you will not be responsible for that material in the quiz. But I think we will definitely get through this. So we had left off last time arguing that together, the first and second order conditions were sufficient to guarantee that we were identifying some sort of profit maximum. Not a minimum, not a saddle point. And we know that when we were looking at the problem from an output-oriented perspective, the first order condition involved the value of the marginal product in dollars being equal to the wage in dollars, right, the nominal wage. And we took the second derivative to think about imposing the second order condition. And we recognize the second order condition involved this term P times F double prime of L. And we required, in order to guarantee that we are at a maximum dealing with the frown face shape of that function and not a minimum, that required that the second derivative with respect to labor was negative. Okay, now, given that prices cannot be negative, right? Prices are going to be positive. That meant the term that had to be negative here was F double prime of L, the second derivative of the production function. And that should be a familiar condition. Okay? When the production function's derivative is diminishing, and when the marginal product is getting lower as we increase the level of input usage. That is absolutely how we define the technological restriction of the diminishing marginal productivity of labor. That's exactly how we define it. So if you have a technology that satisfies diminishing marginal product with respect to that short run input, okay, then that means you will automatically satisfy the second order condition. And you can be confident that just using the first order condition, you will be identifying a profit maximum. All right, so the first order condition, just to kind of reiterate what that means is we're looking for allocations where the profit function is flat. Okay, we saw that can occur at minima, that can occur at maxima, that can also occur at saddle points where the function maybe flattens out but does not necessarily reach a min or a max. Those can happen. So when we employ the FOC, we could identify any of those three situations. Intuitively, we suggested, well, that will occur when the marginal productivity of the last worker is equal to the real wage paid to that last worker. We also argued the same condition last class nominally also applied if you multiply through by price. And we showed that the second order condition meant that the profit function is concave down. It has that frown face shape. What that implied for us, we saw a moment ago, was that the marginal productivity of that input had to diminish, right? The second derivative of the production function itself had to be negative. And what that actually implies for our purposes is that it really restricts us in a way where if we want to analyze profit maximizing behavior and we want to use these types of economic models to do it, this particular restriction where we can only think about technology that satisfy diminishing marginal product means that we're not going to be able to consider any broad class of technology when looking at profit maximizing behavior if we want to consider firms that are facing well-defined problems. So we don't want to really deal with situations where the optimal solution has the firm like producing nothing, or the optimal solution has the firm trying to produce an infinite amount. And I think we might have left off last class looking at a case where the second order condition is violated. Right? Here's a situation where diminishing marginal product is violated globally. Okay, globally means for any value of L, not just for some values, and then it satisfies it for other values. And we argued at the end of last segment that the solution to this problem, given that we don't have a great technology in terms of it satisfying that diminishing marginal product of labor condition, we saw was for the firm to arbitrarily scale up output to an infinite level. And we thought about this in terms of looking for an isoprofit curve tangency. Unfortunately, if our goal was to get to the highest isoprofit curve, you'll notice there is no highest isoprofit curve. We can keep going higher and higher and higher and higher, right? Which implies that the optimal solution in terms of input usage is that L star should be arbitrarily increased towards infinity. Just keep using more workers, you can keep producing more, and you can keep scaling up your profit arbitrarily. Now, we started looking at an alternative perspective on the first order condition last class, where we were looking at the problem rewritten after solving cost minimization and getting that cost function in a way where we could write the problem where our only choice variable was the quantity produced, output. Okay, so we thought about orienting the problem this way: cost on the vertical axis, or dollars on the vertical axis, quantity on the horizontal. And we again wanted to take the first order conditions here. Okay, our objective function was the difference between total revenue in the orange and total cost in the blue. So it's not too much of a surprise to interpret the derivatives of those components here respectively as the marginal revenue and the marginal cost, right? That's our usual first order condition. And we saw last class that because total revenue was linear in Q, it was just P times Q since we were assuming P was constant. This was actually a very special case where the total revenue, or sorry, the marginal revenue function is actually constant and equal to the price that is prevailing in the market. Okay, what this means is that if we wanted to think about a firm that exhibits no market power, right? You're this drop in an infinitely vast ocean of sellers. I'm going to suggest that this fact in the yellow box here, what that is telling us is that from the perspective of the firm, like the firm is a very small drop, right, in an infinitely vast land, okay, ocean, if you will. And the firm, because of that, it can't see the entire ocean. Ocean is too big. All the firm can really see is like the beach. Okay, so there is a market demand curve out there, but the firm does not observe that. All the firm observes is the current market price that prevails. And the firm recognizes no matter what it produces, it cannot change this price. Okay, so this is not the market demand curve. This is the demand curve from the price-taking firm's perspective. And I'm going to call that the residual demand curve. That's like what's left over for us if we account for the structure of the market we're in. This is the residual demand curve from the firm's perspective. Now, why is this consistent with the idea of no market power? No market power means the firm cannot change the quantity it is producing in a way that affects the price. Which means if we produce a low amount like QA, right? In fact, if you wanted to push, forget about this picture, suppose you're the seller of a good and you want to drive the price down. I'm not going to worry about why, but suppose you want to drive the price down, maybe to hurt your competitors. What would you do to your production levels if you wanted to, let's say, drive the price of oil down? If you're the producer of oil, what would you do? Yeah, like try to produce a whole lot more. Yeah, flood the market with oil. Okay. Now, I want you to look at this picture. If my demand curve is flat and I try to flood the market, if I'm a very small entity compared to the whole market, my action is going to be very negligible. And you'll notice if we produce a little bit like QA, or we produce a whole lot like QB, it doesn't matter how much we produce here. Any quantity, what will be true about the price if we face this residual demand curve? Yeah, it's not going to change. And yeah, Dylan asked a really good question. Question is, at what size of the market does it have to be in order for this to be true? And we don't really have an answer to that. This could depend. Okay, what it really depends on is the behavior of the individuals. Okay, so for example, when you go into Vons, right, you don't really try to haggle at the checkout counter, probably. Right? You're at the grocery store. How do you behave? You do something you probably should not do on a used car lot. You pay sticker price at the grocery store, right? You go down the aisle, You look at the price and you decide, given that price, how much you're going to buy. Hey, you don't try to buy up the whole store to force the prices down, right? You're very small compared to the whole customer base of Vons. So when you go into the grocery store, you recognize there's no action I can really take to affect those prices. And because of that, you behave like a price taker. Yeah, I'm going to argue that in many situations, firms recognize, hey, the market is very, very big, and I can't really influence the overall market price. So I treat it as given like this, and I behave like a price taker. Now, at some point, if there's few enough firms, the firms will look around and say, hey, there's not that much competition. And I can see what they're doing. They can see what I'm doing. And now we're strategically intertwined with our actions. And you need a whole nother course called game theory to analyze that type of a situation. So this assumption that the markets are really big, it might seem unreasonable. The reason why we're actually assuming that is to make your life easier right now mechanically. There's a whole nother mathematical toolkit we would need if the buyers and the sellers were not behaving as these price takers, which you assume they do in like Econ 1, right? Econ 100A, Econ 100B, but you will relax that assumption if you get to Econ 100C. So here's what we're going to look at. An alternate perspective on the profit maximizing solution. We have this price that we're taking as given. We have this red residual demand curve. That is the demand curve from the firm's perspective. And we want to solve the optimization problem here by examining the first order conditions carefully. Okay. So we're going to take the first order condition to find Q star. And a moment ago, we just said what that does is it gets marginal revenue minus marginal cost equals 0. Marginal revenue is the same as price. So that first order condition, what that boils down to is we should keep producing until the cost of the last unit is just offset by the price of that last unit, right? Where the benefit of the last unit exactly is offset by the cost. Now, if you look carefully at the picture, what's the trouble with applying that first order condition here? What do you think? So careful, it's not the profit function we're graphing in the picture. So we're not looking for a tangency. What we want to do here is we want to make sure we're applying that first order condition where the price, which is measured by the red line, right? The price is the vertical axis. Okay, and the marginal cost is here in dark blue. Yeah, so I see a lot of folks are saying, oh, that being the case, it looks like there's multiple solutions to the first order condition. Multiple solutions. There's this allocation here, QA, and there's this allocation here, QB. And we've seen a similar idea in the last segment when we had the problem oriented with respect to the choice of labor. Okay, so this raises an important question, and that is, well, if we have multiple solutions to a first order condition, which of those solutions is the right one, right? Which of these things is profit maximizing for us? Okay. And the logical test we're going to use here, I think, is a good intuitive one. I want you to think about maximizing profit as kind of like you're trying to climb to the top of the profit mountain, right? You're trying to climb to the top. Okay. And if you are at the top, already, one easy way for us to check is that if you're at the top and you walk in any direction, what will happen? Yeah, your elevation should drop, right? If you're already at the top and you change your position in any direction, then your elevation should drop. So what we're going to do here is we're going to assume we're at the top of the mountain. And then we're going to move around. And if the only thing that happens to us is we fall, then we can be confident that we were at the right solution to begin with. But if we move around and we find that we've gone even higher than where we were standing, then what must be the case? Yeah, that's right. We must not have been at the highest point. Okay, so let's first put ourselves at QA. Let's put ourselves here and think about what happens if we take a little bit of a step to the right. We're at QA. We're going to think about taking a very small step to the right. And if we move to the right, what happens to the marginal revenue of the next unit that we were going to sell? Does that change? The marginal revenue, the curve in red. If we produce a little bit more, does that change? It does not, right? That red curve, that flat demand curve, that marginal revenue curve, that stays constant. I produce a whole lot, I produce a little, try to flood the market. I'm tiny, I can't affect the price. That is why that happens. Okay, so if we produced a little bit more, the revenue stays the same to the right of point A. But what happens to the cost of the next unit if I was going to produce a little bit more? Yeah, it goes down. So revenue stayed the same. They were equal a moment ago, but we move a little to the right. The cost drops, which means on that next unit, we start to make a what? Yeah, that's right, Keegan. We do start to make a marginal profit on that next unit. So the revenue on the next unit stayed the same, but the marginal cost actually went down here, right? It was decreasing. And because of that, that meant by moving a little bit to the right, we're able to make a marginal profit on that next unit. There it is. A little bit of marginal profit there. Okay. So here's what happened. We asked ourselves, hey, we're standing at QA. We think QA is the top of the mountain. It satisfies the first order condition. But we moved a little bit to the right. And what do we just argue happens to our profits? Yeah, they go up. What does that tell us about QA? We were standing there, we moved, and we were higher. Yeah, it cannot be profit maximizing. In fact, do I want to stop at QA or should I go farther? Should we keep walking? If I go a little farther, the cost goes down even more. Is that right? So the next unit, we get some more marginal profit that we add to our bank account. Then we get even more marginal profit that we add to our bank account. So as we keep producing these units between QA and QB, hopefully everyone agrees, we keep moving up the profit mountain. This is additional profit from producing all of these extra units in this interval between QA and QB. So I'm going to argue A is definitely not a profit max. Okay. What about B? What about B? Well, if we wind up in a situation like we were at A, all right, we saw we could increase and sell more units because the marginal revenue exceeded the marginal cost on those units. If that ever happens, if the revenue on the next unit exceeds the cost, you should produce that. You will make a marginal profit. Okay, so A, we've argued here, is not profit maximizing, but it does satisfy the first order condition. And if it's not a max, it might be what? That could be a minimum. It's actually exactly what that is then. QA is actually a profit minimizing allocation. So again, we got to be a little cautious just applying our first order conditions without thinking about them carefully. Now, if we were standing at QB and we moved to the left, hopefully everyone would agree that we would miss out on some of that green region we were looking at a moment ago. So if we move to the left from QB, definitely our elevation on the profit mountain drops. What happens if we move to the right relative to QB? Right, the revenue stays the same, but what happens now? Yeah, marginal cost is like increasing, right? So if we move past QB to the right, we're going to start making a marginal loss on those units, right? The marginal cost exceeds the marginal revenue. So that's adding some profit loss to our bank account, right? And every unit I produce past QB, it looks like the cost is getting higher and higher. So that profit loss is getting bigger and bigger and bigger. So if you're ever in a situation where the marginal revenue is less than the marginal cost, right? We don't want to produce those units. We want to cut back. We're producing too much. So we argue that if we took a step to the left of QB, we miss out on some profit we could have captured. Our profit goes down. If we step to the right of QB, we start making extra losses on those units and our profit goes down. Therefore, no matter which direction we moved from QB, our profit went down. Therefore, the conclusion is what? What's the conclusion here? Yeah, gotta be profit maximizing. Absolutely. QB is a max. Hey, by the way, if you go to the left of QA, you will also make losses on those units at the margin as well. So going from 0 to QA, your profit's going down, 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 down. Then you get QA. And if you start going past QA, then you pick up that green region, which brings your profit back up. So we've argued here, I think pretty reasonably, that Q star has to correspond to QB in this situation. And I'm going to show you that QA actually is a profit minimizing solution here. So again, we have to be a little cautious about applying the first order condition. Here is what we're looking at, but from an output oriented perspective. Right? QB, that put us at the top of our profit function. We were at the top of the hill there. But QA, unfortunately, put us at the bottom of the valley, not at the top of the hill. Okay, so just like we had done with respect to the input-oriented problem, where we had L on the horizontal axis, we could think about second-order conditions that will be relevant for this particular dual problem specification, where you have the output variable measured on the horizontal axis. So we're still talking about that second-order condition, right? If we're maximizing profit, right? If we're here, then what has to be true? Well, MR has to equal MC. But it is not necessarily the case if we reverse that just because MR equals MC, that does not necessarily guarantee that we are at a profit max, right? Like QA, MR equals MC, but QA is not profit maximizing here. All right, now, our first order condition, right? The first derivative of the profit function gave us the difference between the marginal revenue of production and the marginal cost. So if we wanted to impose a second order condition here, we can do that. If we do that, then I have to take the derivative of the marginal revenue and the derivative of the marginal cost. And our second order condition was that we had to have that frown face profit function, meaning it needed to be negative. Now you'll notice this condition here, the second order condition, generalizes pretty nicely if we add that negative marginal cost term over to the right. And this tells us that we will satisfy the second order condition as long as the slope of the marginal revenue curve is less than the slope of the marginal cost curve. Okay. Says the second order condition is satisfied as long as MR prime. In fact, let me clear this here. We have MR prime, which is the slope of the MR curve, that needs to be less than MC prime, which is the slope of the marginal cost curve. Yeah, Isaac, you're like one step ahead of me. On fire today, my man. Nicely done. You're absolutely right. Isaac is saying, well, if you look at that red marginal revenue curve, the slope of that thing is pretty darn flat. Slope of that is equal to what? Yeah, slope of the MR curve is equal to 0. So we could absolutely plug 0 in on the left-hand side of that relationship. Is that right? So the second order condition here, let's think about how to interpret this. I'm going to highlight it in green. Sorry, wrong green. I'm colorblind today. Here we go. Second order condition for the output-oriented version of the profit maximizing problem is telling us we will satisfy the second order condition as long as the slope of the marginal cost curve does what? Yeah, as long as the MC curve slopes upwards. Okay, so you should be able to note if you're looking at the marginal cost curve, at QA, it is not sloping upwards, it's sloping downwards. It does not satisfy that condition at QA. But at QB, it certainly does. It is upward sloping. It does satisfy the second order condition, which is why QB is the max and QA is not. Okay, so to reiterate, right, first order condition says profit function is flat. We interpreted that first order condition to mean that the marginal revenue equals the marginal cost, right? Or price equals the marginal cost in that case where we have a flat residual demand curve because we're a perfectly competitive firm. Second order condition says the profit function had to be concave. And when we just imposed that condition a moment ago, we saw that implied that the marginal cost curve has to be sloping upward at a profit maximizing allocation. That means if we have a technology that does not have an upward sloping marginal cost curve, then we can't really think about that technology as yielding a well-defined profit maximizing solution. Okay, so let's go ahead and take a look at an example where we get a weird, I'm going to call this a degenerate solution. This is a type of technology that we're not going to be able to use to analyze profit maximization. Let's go ahead and consider the case of a firm with a flat marginal cost curve. This means they have constant marginal cost. They also have constant average cost in this case if there's no fixed cost, but we'll just leave it at this for now. And you might remember this as a case that happens if you have constant returns to scale technologies. You get a linear cost function, so the slope of it winds up being constant. Right now, let's think about what the solution of profit maximization would be first in this case one, let's suppose our cost is here. So if this is the situation, what is true about the marginal profit on any unit you will make? Yeah, it's constant. And more importantly, it has what sign? I agree on all. Yes. Yeah, it's positive. So if I produce that first unit, I get some positive profit at the margin. The second unit gives me some more profit at the margin, so on and so forth. So if this is the case, what is the solution to profit maximization? What's the Q that maximizes profit? I'm arguing it's not any point. Hey, if you stop here, that's not as much profit as if you produced here, which is not as much profit as if you went here. So it's not any point is equally profit maximizing. That's not what we're looking at. If this is the situation, every unit gives you the same amount of profit, and that doesn't diminish, then how can you make as much profit as possible? You try to sell as many units as you possibly can, right? Sell an arbitrarily large amount. Okay, so the solution here is not a great one. It's not really well defined. A firm wants to kind of explode itself and produce an infinite quantity and demand infinite labor to do that. Now, suppose the price was below marginal cost. Let's consider this case. If P is less than MC and I sell any unit, what will happen to me? Any unit is going to cause a loss, right? Loss in the first unit, loss in the second. I'm digging myself deeper and deeper and deeper into a hole. So if this is the situation, what is the solution to the profit maximization problem? Well, so if we're in the short run, I can't necessarily leave the market. That's a nice idea, but maybe I can just turn off the factory and not produce anything. Okay, I can shut down. So yeah, let's produce the lowest amount of Q. What's the lowest you can produce? 0. So this is a totally degenerate solution here. Here, we're not getting any well-defined profit maximizing behavior either, right? What does the firm want to do? It either wants to produce an infinite amount or produce nothing. Okay, there's a third case. I'm going to also argue is not super interesting for our purposes. I'm not even going to draw it. The third case is, well, what happens if price and cost were equal? What would be profit maximizing in that situation? Dylan, I think this is where your solution comes back to play. Yeah, P and MC, if the red and the blue lines are right on top of each other, every unit makes you 0 marginal profit, which means it doesn't matter how many you produce. You're making 0 profit. Anything would be profit maximizing because they all generate 0 maximum profit for you. Okay. So here was a degenerate case where we did not have an upward sloping marginal cost curve. And because of that, we're not getting a well-defined solution to the profit max problem. Now let's go ahead and make sure we can diagrammatically identify profit and loss situations. Okay. In fact, we looked at first and second order conditions, right? We were writing out the problem as an output choice variable. We took those first order conditions. Right, we saw we got this familiar condition, price equals marginal cost. And what we're able to do is use that first order condition to figure out the optimal level of output. Yeah, so in that last case where P is equal to C, the firm could do anything. It doesn't matter. Anything is optimal for the firm in that situation, which is why it's not really an interesting case to think about. Okay, what's the optimal thing? Anything is optimal in that case because you can't make any profit, so it doesn't matter what you do. Now, what we're going to look at is the idea that this first order condition, provided it is well defined and we have a second order condition that's satisfied, I'm going to argue that what that does for us is it defines an important relationship that tells us how much we should supply given the market prices, which is literally a supply curve. Is exactly what that is. So we're going to think about deriving the supply curve in just a moment from the firm's perspective. And this is something you might have done in Econ 1, but we're going to take another closer look at it. And before we do that, I want to ask the question, how much profit is the firm making? Okay, we know they're making maximum profit, but that could be a negative number. Could be zero. Could be a positive number. Right? I want to compute that. And unfortunately, we don't have enough information to calculate the total cost. Okay. You might say to yourself, well, we took the total cost and we took the derivative to get marginal cost. So can't we work backwards to go from marginal cost to total cost, right? Couldn't we work backwards? What operation would that require? Yeah, so what's the inverse of taking a derivative? Yeah, we could think about maybe integrating the marginal cost to get the total cost. Right? If we take the derivative of total cost to get marginal cost, then if we integrated marginal cost, we might get total cost, but we have to be careful. You might remember from calculus, and it was a super annoying thing. But when you had an indefinite integral, there was this extra thing you always had to carry around at the end of the integral. You guys remember that? Yeah, Almo remembers. Keegan, yep, at least that plus C, that constant. Okay, unfortunately, if we integrate the marginal cost curve, that plus C pops out. Anybody know how we interpret that in this case? Like integrate marginal cost to try to get total cost, but there's a constant part of total cost that pops out. What is the constant part of the total cost function? Yeah, Dylan, I like what you're saying. Dylan T. Yes, it is the fixed cost. That's exactly what it is. Okay. So I'm going to argue that we can't actually get the total cost function here because we don't know the fixed cost. If I knew the fixed cost, that would be the value of that constant of integration. That would be it. Okay. So here's what we're going to do. If we don't know the fixed cost and I want to calculate profit, I can do this if I know where my average cost curves are, right? Here are my average costs. Okay, I think now it's easier for us to think about how much profit does the firm make. Okay. So let's go ahead and rewrite profit in terms of the average cost. Right? This term in green is the average profit per unit. Average profit per unit. And then we multiply that by Q, which is the total number of units. And then that should give us the total profit. Is that right? If you distribute Q in, you should get total revenue minus total cost. Okay, so if we look at our picture and we follow Q star up to the average cost function, just go up to the average cost function. So we'll go up here, and we'll go straight over. And that'll tell us exactly what our average cost is per unit. Now, my question is, are we making a positive amount of profit per unit or not? Okay, good. A lot of folks are saying, yes, we definitely are because P is above AC. So that is the average profit per unit. If we want to calculate the total profit, then all we have to do is take that green distance and multiply it by what? Yeah, we'll just multiply it by Q. Exactly. Very good. We'll multiply by the number of units we're producing. And that is this horizontal distance here out to Q star. Everybody comfortable with that? So if I take the height of this rectangle, and then I multiply it by the base of this rectangle, then that green region represents what? Yeah, that is the total profit that we're making in that solution. That's exactly right. Now, let's suppose for a minute something happens in the market and it causes the price to drop. Okay, suppose the price drops. And if the price drops enough, okay, we should be able to see that instead of making a positive profit, this can cause the firm to incur negative profits, also known as a loss. Okay, and all we're going to do here is we're going to apply the first order condition, and we're going to find the new optimal bundle at the lower price, right? Which means I want to find that part of the upward sloping marginal cost curve where P equals MC. Hopefully everyone's comfortable seeing that that occurs right here on this yellow dot that I've highlighted. And then we can again go up to our average cost curve from Q star. And what's happening now if you compare the average cost to the price per unit? Yeah, we're taking losses now, right? Average cost is higher than the price we're selling things for. Which means if we multiply that by the number of units we're selling, okay, then that area now represents the total loss from producing a Q star. Now, just to be clear, this is the best we can do. Sometimes the best you can do involves making a loss. Okay. And you're probably asking yourself, well, given that we're making a loss, it might not be a good idea to stick around in business. But you have to remember, we're in the short run. And in the short run, I can't do things like sell off my factory. I can't change my capital allocation. Best I could do is I could shut the lights off and tell my workers not to show up. But I'm still stuck paying my rent. That's a sunk cost. Okay, so question is, should the firm shut down in this situation? Okay, should the firm shut down? The answer to this question requires us to think about the benefits and costs of shutting down. Okay. So in the short run, I can't sell my factory, but I can send everyone home and turn off the lights. Okay. But I still have to pay that sunk fixed cost. My rent, that's gone. I paid that. Whether the workers are there or not, I'm paying for my factory. Now, I want to think about the benefit of shutting down. If we shut down, what are we saving ourselves? Okay, I don't have to pay wages. I like that. Wages are a type of which cost? Yeah, they're variable. So if I shut down my cookie factory, I'm not using cookie dough anymore. I'm not using workers. No more chocolate going in there, no sugar. Okay. So the benefit of us shutting down in the short run is we can save that variable cost. Unfortunately, The fixed cost cannot save that. That is sunk, never getting back unless you can, like Johnny be good yourself back in time in a time machine. Not happening. Okay, so that's the benefit of shutting down. We save ourselves the variable cost. What is the downside of shutting down? What can't we capture anymore if we shut down? Yeah, Elise, I like what you're saying. Very astute. Very good. Okay, the implicit cost is we're not going to be able to capture any revenue if we're shutting down. So what we need to think about in terms of whether or not we should shut down is, does the benefit of shutting down outweigh the cost of shutting down? Okay, so our shutdown ruler, I'm going to try to give you a very intuitive way to think about this. We want to shut down if the benefit of shutting down, the variable cost, is greater than the total revenue. If that's the case, you shut down. If the ingredients it costs you to make your cookies are more than what you can get from selling your cookies, you should not be in business. Okay. Now, let's suppose we divide both sides of this equation by Q. If I divide variable cost by Q, what does that become? Yeah, average variable cost. That's right. And if we divide total revenue by Q, right, which was P times Q is total revenue. If we divide that by Q, then we get what? Yeah, then we get our price, right, which was equal to marginal revenue. So if we divide both sides by Q, I think you will get a familiar condition that we should shut down when the average variable cost of production, if that is bigger than the market price, then you can't make a profit at the margin. It's not possible. Right? You're not going to be able to, you will not be in business because the benefit of shutting down exceeds the cost of shutting down. The cost of your ingredients is not covered by what it is you're selling. So if you look at this picture, okay, will this firm shut down? If we go up to the AVC curve from Q star, let's do that. We go up to the AVC. There's the AVC in the purple. Are we going to shut down if we're the firm in this picture? Yeah, we're not going to shut down. We're going to stay in business. Okay, in fact, there's a special point where we would shut down, and that point happens to be at the very bottom of the AVC curve. The actual shutdown point here, it's at the very bottom of the AVC curve. That's where we would actually want to shut down. If the price ever dropped below that, then we would want to shut down. Good question. Question is, are the AC and AVC curves given in these types of problems? I might give you a cost function or a technology, and you can find the cost function and you can find all those curves. So in some regard, yes, they have to be given. Absolutely. But they'll be given in a way where you'll be able to find them. So here was our shutdown rule, which we simplified. And if I subtract AVC to the left, and I multiply through by Q. If I was to multiply this by Q, anybody know what we would get? You get total revenue minus total variable cost, but not including fixed cost. What is that? What is that? Yes, that is producer surplus. So the shutdown rule here is pretty simple. if you're going to get a negative piece of pie, don't eat it. Right? Producer surplus is the piece of the gains from trade that sellers get. We argue maximizing that and maximizing profit, same thing. If the producer surplus is negative, just stay out. What's better than eating a negative piece of pie? Just don't eat any pie. Okay? So these are all equivalent conditions. The firm should only shut down in the short run if it would make negative producer surplus from operating, right? Those fixed costs are sunk. We can ignore them. Okay, and just think about, are they making producer surplus or not? Okay, so we said a moment ago that this firm on the right will not be shutting down, okay, because the price is above that shutdown point, okay, the minimum of the average variable cost curve. And price is above that minimum. Now, let's wrap things up tonight by thinking about deriving that short run supply curve. Okay? And to think about this, what we're going to have to do is consider how the firm would change its profit maximizing supply decision by looking at different price situations. What happens if the price changes? Well, the profit maximizing quantity will change. So let's go ahead and consider 3 different price situations. We had this low price we looked at a moment ago, where we said, yeah, they would still produce even though they were making a loss there. We had a higher price that we considered just before that, where they were definitely making positive profit. And if the price went even higher than P2, hopefully you would agree they will still be making positive profit. Okay. And notice at each of these allocations, we're applying which condition here? Yes. That is the first order condition. That's identifying those points. Now, which function are we tracing out as we move the price around? Which function is getting traced out? Anybody see it? Which function? Yeah, it's the marginal cost function. Everyone see that? We're kind of, as we move P around and we apply that first order condition, we're tracing out the marginal cost curve. Okay, however, we just argued a moment ago, if the price goes low enough below the ABC, right, below this shutdown point in purple, then how much should the firm produce? Exactly. And it shouldn't produce anything. Okay, so if the price falls below that purple point, okay, the minimum of the ABC, it's not a perfect diagram. Don't worry about the scale of it. But if the firm chooses to shut down, then that means when the price is any lower than that purple point, okay, we're not going to be tracing out the marginal cost curve anymore. We're going to be tracing out what? Yeah, we're going to like jump and we're going to be up against the axis at 0. So here's what happens. Okay, the short run supply curve of the firm. Okay, part of that is the marginal cost curve that is above the shutdown point. However, if the price drops below the minimum of the ABC curve, if it goes below that shutdown point, then we argued you're not going to be producing anything, which means the supply curve looks like it's along the marginal cost curve until we get to that purple point, and then it jumps over to the horizontal axis, sorry, over to the vertical axis rather. Okay, so this locus of points that we're looking at in the flashing yellow region, what is that? That is literally the firm's short run supply correspondence, or short run supply curve, if you will. That is the firm's short run supply curve. So note, it's not the whole marginal cost curve. It's not the whole marginal cost curve. And you might remember assuming in like Econ 1 that supply curves were marginal cost curves and that demand curves were marginal benefit curves, right, for consumers. Okay. Now we can see why that is in fact the case. Supply curves are measuring the marginal cost of production. That's what the firm looks like to do its cost benefit analysis in defining its optimal supply decision. So here is where we are at. We've just showed that the firm's short run supply curve, it is the marginal cost curve, but it is specifically the part of the marginal cost curve that is above the minimum of the AVC. It is not the entire marginal cost curve. It's the part that is above the shutdown point. Okay. Below the shutdown point, the firm's optimal short run supply is to turn off the factory, close the doors, send everyone home, and produce zero. All right, so we have a little bit of time left today. So what I'm going to do is I'm going to start discussing some details associated with the second order condition. These will not be quiz relevant for this coming week, but they may be in the future. So I believe this is about where the last slide deck ends that you have access to. So that is all I will hold you to for the quiz. You should be able to think about where this short run supply curve comes from. And there are several questions in the problem set. Problem set 3 is likely very relevant right now. There are probably questions on practice exam 2 that are relevant to short run profit maximization that I would recommend you look at in preparation for the quiz on Monday. So with that being said, let's talk about this. We saw a moment ago that we could think about the short run problem really from two perspectives. We could write the problem out as a function of L, where the second order condition required that we have diminishing marginal product of labor. We also saw that we could in dual write the problem out equivalently using the cost function specification and write it out with the objective function defined with the choice variable being quantity, right? Quantity of output. And in this case, we inspected the second order condition associated with the first order condition for optimization. And the second order condition really boiled down to the firm having a marginal cost curve that's sloping upwards. Okay, if we have marginal cost curves that slope upwards, or we have technologies that have diminishing marginal product, then we will have a reasonably defined profit maximizing condition, okay, or solution to that problem. Now, the question is, how are these things related to each other? How are they related? And what I'm going to do here is I'm going to make a very mathematical argument in a moment that when the second order condition holds on the left, then that implies also the second order condition on the right holds, even though the problems are written in different orientations. One's in terms of labor as the choice variable, one's in terms of the quantity of output as the choice variable. So here is the proof we want to think about. In fact, let me ask you guys, I'll give you the option. We can go through this tonight, or we can save this for next class and maybe get out a little early. I will leave it to you. You let me know in the chat. Okay. Looks like pretty overwhelming support for saving it and getting out early. So let's plan on doing that. Okay, it is 7:40. Let me go ahead, open things up for some rapid fire Q&A here. Otherwise, you are free to go. Have a wonderful weekend. LRP is coming out after this evening. Quiz on Monday. And take care. Enjoy your weekend. Hope you're all doing well and staying safe. If there are no other questions, then let me hand things over here to our wonderful UIA, Uday.